In this last part of the present chapter, we are going to discuss something about special integrating factors and transformations. Let's recall that we started the chapter with this equation, m dx plus n dy equal to 0, where both m and n are functions of x and y. And the first type of such equations that we considered is exact equations. If this equation is exact, then there is a definite procedure for solving it, and following that procedure we can find a one parameter family of solutions. We already know how to do that. But we also saw at that time that not all equations are exact. However, even if an equation is not exact, sometimes we can multiply it by a function to make it exact. Make it exact means to turn it into another equation which is exact, and then we can solve that equation. That function is called an integrating factor. And we saw examples of this also. However, at that time we wondered how one could go about finding such an integrating factor, or if a specific non-exact equation is given to us, whether there exists an integrating factor. At that time we did not really offer any answer, but we just said that we are going to say something later on. So now the time has come again to address this problem, and let us see exactly what is stopping us from giving an integrating factor to such a general equation which is, say, known to be not exact. Say this equation is not exact and I want to find an integrating factor. What's the problem? Let's investigate. So we seek an integrating factor which itself is also, like m and n, a function of both x and y. So I am calling it IF, means integrating factor. We want to find an integrating factor which does what? It does this, that if you multiply this equation by this integrating factor mu, then the equation becomes this: mu m dx plus mu n dy equal to 0. This should be exact, and we already know when such an equation is exact. I mean, we found one criterion for that. If you remember, I'm going to write that here now. So we are going to apply that criterion to this equation, assuming that it's exact, and then let's see what that gives us. And that criterion is this. This equation means this equation above is exact if the following condition is satisfied. The partial derivative of mu times m with respect to y equals the partial derivative of mu times n with respect to x. I did not again write x comma y to save space. I mean, you already understand that mu, m and n are all of them functions of both x and y. But now what do we get out of this condition? Now this is what you get from this condition. Whether you are doing ordinary differentiation or partial differentiation, product rule is just product rule. So the left hand side becomes this. First you say differentiate mu with respect to y, keeping m intact. Then in the second term you keep mu intact and differentiate m with respect to y, partially of course. So that's how you get this left hand side. And similarly you get the right hand side here, again using product rule. But this time differentiating partially with respect to x. So this is now you have. And from this, if you want to know what mu is, you have to solve this equation for the unknown function mu. Note one thing carefully, that we are given this equation, we start with this equation means that we already know m and n. These are known functions. Mu, however, is the unknown thing that we want to find out, so that this equation becomes exact. This is not exact, that's already given. But we want this to be exact, for which this happens, and for this one happens. So now if you solve this for mu, then mu will be found. But this is a partial differential equation in mu, and in general we don't really know anything about how to solve a PDE, partial differential equation, at this stage at least. So that's the difficulty. But in spite of this difficulty, can we make the situation a bit simpler? Say we arrange things in such a way that still mu can be found. Let's see. Say we aim for this simplification. Suppose mu is a function of x only. We see that it's not really possible for us, at least now, to solve this general partial differential equation to find mu as a function of both x and y. But say we want mu to be only a function of x. We will lose the ability to solve many equations by finding the appropriate mu for that equation if we impose this extra restriction on mu. But because we cannot do anything in the general case, so let us see what we get out of this simplification. Now what will the effect of this be on this equation now that we want mu to just be a function of x? In this case, this equation turns into this. Why? If mu is only a function of x, then this partial derivative vanishes, it becomes 0. So we are left only with this on the left hand side, del m del y times mu. What happens on the right hand side? Not much. The only change is that this partial derivative turns into ordinary derivative because mu is a function of x only. So d mu dx times n plus del m del x times mu. And then we subtract this term, this second term on the right hand side from both sides. So that's how we get this equal to this minus this times mu. And this equation takes on this equivalent form. D mu divided by mu equals 1 divided by n if you transfer the n over to this side times this difference times dx. Now can we integrate this equation to find mu? Well, if you want you can integrate the left hand side, that will give you ln of mu, natural logarithm. But for the right hand side to be successfully integrable in the sense that you can carry out the integration provided this thing is a function of x only. In that case you can do it. And then I give a name, a small name to this part, 1 over n times this difference, let me call it star. And this is the condition, if star involves only x but not y, then we can integrate both sides because then the right hand side will involve ordinary integration with respect to x of what? Of this function which will then be a function of x only, and that is this integral. And the left hand side will be ln of mu, from which if you solve for mu, you will get mu like this. Mu equals exponent of that integral. So this will be your integrating factor if this happens, if this is a function of x only. And if you then go and multiply the original equation by this integrating factor mu, then that will turn the original equation into another equivalent equation that will be exact, and then you can solve it. So we can summarize our discussion in the form of this theorem. Consider this differential equation. I have written it briefly, m dx plus n dy equal to 0. You already understand that m and n are both functions of x and y. All those things are there in the background. If this involves only x, then an integrating factor means an integrating factor for this equation is this. And there is another part of this theorem also. And that second part is this. If instead this other expression involves only y, in that previous expression we had 1 divided by n times this minus that. Here, however, we are having 1 divided by m times this minus this. If this expression involves only y, then again an integrating factor for this equation is this. The integral of this with respect to y, because it's a function of y only, and actually not just that integral, the exponent of that integral. So that is our theorem. Now let us see an example based on this discussion. And that example is example 218, where we are going to consider this differential equation. 2x squared plus y times dx plus x squared by minus x times dy equal to 0. The author mentions that this verify that the above equation is not exact, separable, homogeneous, linear or Bernoulli. It's none of those things. So comparing this equation with the general equation m dx plus n dy equal to 0, we get this. M is 2x squared plus y and n is x squared y minus x. Now let us concentrate on this expression that we saw in that theorem. It is one of the two possible expressions. 1 divided by n times del m del y minus del n del x. So n is this, so 1 divided by this times. What do we get if we partially differentiate m with respect to y? This contributes 0 because there is no y. This one contributes 1. And partially differentiating n with respect to x, we get 2xy because y is considered constant. You are differentiating partially with respect to x. X squared gives you 2x and y remains, and this term gives you 1. So you get 2, that means 1 minus of minus 1 is plus 1. 1 plus 1 is 2. 2 minus 2xy, that is 2 times 1 minus xy divided by this denominator. If you take minus x common out of the denominator, the other factor is 1 minus xy. After cancelling these two things, this is what you get, minus 2 divided by x. So you see that really in this case, this is a function of x only. So we can find an integrating factor. And that integrating factor is this. Exponent of integral of this thing minus 2 divided by x with respect to x. Now if you do the calculation, I am not going through the calculation, you can do it yourself. You get 1 divided by x square. So this is our integrating factor. Now what we are going to do, we will multiply this equation on both sides by this, and that will turn it into an exact equation. So when you do the multiplication, this is what you get. If you multiplying by this means dividing both sides by x squared. So you get 2 plus y divided by x squared times dx plus y minus, after cancelling 1x, you get 1 over x times dy equal to 0. And as promised, this is really an exact equation, which this calculation shows. To see whether it's exact, you apply that criterion. You differentiate this one partially with respect to y. What do you get? This is of course constant and x is constant when you are differentiating with respect to y partially. So you get 1 divided by x squared. And you also simultaneously differentiate this partially with respect to x. The first term contributes 0 because it's y, it does not have x. And differentiating minus 1 over x, you know from calculus, you get 1 over x squared. So yes, it is really exact. And if you solve this exact equation like how you normally do, you will get this one parameter family of solutions. 2x plus y squared over 2 minus y divided by x equals c, where c is the parameter or arbitrary constant. Now the verification of that remark that the author made after giving this equation, that it is neither exact nor homogeneous and all the other types, is left to you. And the solution of this equation and getting this as the one parameter family of solutions is also left to you.